In this video, I'm going to be working some limit examples for kind of at the beginning of AP Calculus. So really at this point, we really only have the definition of a limit. That, a limit exists if each of the one-sided limits exist and agree. So we're going to start with this one, and we're going to find the value of the limit of f of x as x approaches 1, or explain why it doesn't exist. So in order to do that, we're going to look at the two one-sided limits. So I'm going to start with this cosine of pi x when x is greater than or equal to 1. Well, if x is greater than or equal to 1, that kind of corresponds to the limit as x approaches 1 from the positive side. Okay, the limit of f of x as x approaches 1 from the positive side is just going to be cosine of pi times 1. And thinking back to last year, right, we can probably take it a little more simply than we did then. Remember, pi is over here. Cosine is the horizontal displacement from the y-axis. So that looks like -1 to me. So I'm going to say that's, okay, -1. Okay. And then natural log of e times x is the other piece of this piecewise defined function. So if I'm thinking x is less than 1, that will give me information about the limit as x approaches 1 from the negative side. So that limit's going to equal natural log of e times x. And where, I guess, I'll just show you me doing that, where I plug in x equals 1, so it'll just be e times 1. And I'm thinking, okay, natural log of e, what exponent do I put on e to get e? Well, yeah, I could just do it right there. It's e to the first power, so that's going to equal 1. Okay, so the limit of f of x as x approaches 1, in order for it to exist, we would have needed to see the same number from the two one-sided limits, and we're not seeing the same limit. So I'm going to write out that this limit does not exist, and you can write d and e, but I need to give a reason, okay? And really the reason is the disagreement in one-sided limits, but that's really not going to be specific enough. What you need to write is going to be because of the, specifically, the one-sided limit from the left is not equal to the one-sided limit from the right. And you're going to see in this course, the whole, explain thing, that's going to be just as, if not more important than the actual answer itself. All right, number 2 is asking us to find the values of the limit as x approaches 2 from the right and the limit as x approaches 2 from the left. Okay, so just the two one-sided limits. So what we're not going to need is that information about what's actually happening at x equals 2, at 3. And we're not going to need to compare them either to determine if they're equal. No, it would be if we didn't see a one-sided symbol on there. All right, so limit as x approaches 2 from the positive side of g of x. Okay, so it's going to be this one. X is greater than 2. So let's say, first, this thing is going to equal, I'm going to plug in 2, sine of 2 pi over 3. And I'm going to draw myself a diagram. I remember that 2 pi over 3, it's over there in the second quadrant with a 60-degree reference angle. And if you were in AP Pre-Cal last year, hopefully this is starting to come back. This is a thing we did a whole lot. It's a 30, 60, 90, so the legs are 1/2 and root 3 over 2. The hypotenuse is 1. The longer one's root 3 over 2. Think about what's going to be negative. That's going to be this one. Sine's the vertical, the ratio of the vertical leg to the, hypotenuse, so it's going to be root 3 over 2. Then the limit as x approaches 2 from the negative side of g of x. I'm going to use the other piece, okay? Approaching from the negative side, that's where x is less. So that's going to equal e to the 2 minus 2. That's e to the 0. And we know that that's going to equal 1. Okay, this next problem, this is, when I made a new homework, a new set of practice problems. I saw this and I realized really, if I tell you that the limit as x approaches 0 sine of 4x over x is equal to 4, we can use limit properties to, explore some algebraic things. Okay, so what is the limit as x approaches 0 of x divided by sine of 4x? Okay, well, what we know to be true is that the limit of 1 over a thing is going to be 1 over the limit of that thing, just provided that that limit is not going to 0, right? You know, like f of x is going to 2, 1 over f of x is going to go to a half. Okay, and I don't think that's too difficult to believe, provided that the original limit exists and is not going to 0. So in our situation, we might be interested in saying, okay, well, this is just the reciprocal of what we saw originally. So, I mean, it's going to go to 1/4, right? Because this is the limit as x approaches 0 of 1 over sine of 4x divided by x. Okay? And this thing that I'm highlighting is going towards 4 as x approaches 0. It stands to reason that this is going to equal 1/4. Okay, and then in part B, we're going to say, what is the limit as x approaches 0 of 3x divided by tangent of 4x? Okay, we're going to want to use a trig identity on this. But I don't want you to get the wrong idea from this problem. We're not going to need to know a bunch of trig identities. The only ones we really need for AP Calculus are the reciprocal identities. The tangent is sine over cosine. Secant is 1 over cosine, the ones like that. We don't even really need the Pythagorean identities, and if you're in AP Pre-Cal, we really don't need those angle addition formulas. That's just not going to be necessary for this course. This one, what I'm going to do is kind of break it out. Okay, first we've got this 3 that isn't there, but that's just like kind of a multiplier, right? So I'm going to say it's 3 over 1 multiplied by, okay, x over tangent of 4x. I'll switch the tangent to sine of 4x divided by cosine of 4x. All right, so if I'm dividing by that fraction in the denominator, the cosine of 4x will kick back to the numerator, and you could take it off to the side and keep some things, change some things, and flip some things, and you see how it works. I'll let you work those details out. It's going to be the limit as x approaches 0 of, I'm going to bring the cosine of 4x over here. That'll be good. Over 1 times x over sine 4x. Okay, and one thing that we know to be true, the properties of limits, is that the limit of the product is equal to the product of the limits, provided that each of the things is existing individually. So this is going to equal the limit as x approaches 0. I think this pen might be too thick, but it'll be right. 3 cosine of 4x divided by 1. Well, I don't even really need to write that. And I know that's going to exist, right? Because I can take the cosine of 0, and it's not like going to be undefined or anything. And then I'm going to multiply that by the limit as x approaches 0 of x over sine 4x, which we actually just computed in part A. Okay, so cosine of 4 times 0. Okay, thinking back to the unit circle, 0 radians is over here. Cosine is the horizontal displacement from the y-axis. It's going to be positive 1. So I've got 3 times 1, and then it's the first limit multiplied by, okay, well I figured out that was 1/4, so that's going to be 3/4. All right, now we're going to kind of turn this backwards, and we're going to come up with some drawings of some functions that meet a description. I saw this problem set, I don't remember where, but I really liked it. And I think it was definitely something that was missing from my last homework. So the limit as x approaches 1 of this function and the value of the function both exist, but the value of the limit is not equal to the value of the function. Well, okay, let me draw limit existing in blue. So limit existing to me means from the two sides we're approaching the same value. Okay. Function itself might not be defined, or if it is defined, might not be equaling the value we would expect at that hole. And so it's saying a of 1 exists, but the limit is not equal to the value of the function. Okay, well that would just be as long as it was anywhere else, but it was there at x equals 1. And so I could just say drawing some axes. Say that's x equals 1. All right, neither the limit nor the function exist. Well, I think there's a lot of ways for that to happen. You could be creative and draw that any old way. But a couple things come to mind. To me, a vertical asymptote is going to be like, okay, the function's not approaching any one value. It's going to infinity or negative infinity. And the value of the function itself doesn't exist because you've divided by zero. It's the cause of a vertical asymptote. But I think, thinking about these functions that have these like kind of breaks in them, which is kind of keep seeing in the examples, I would say this would be a situation where the limit doesn't exist. And just, provided that I didn't fill in a circle here, or put in a dot anywhere, above x equals 2, that would be b of 2 being undefined, right? There's no actual graph there, there's just holes. And so that would be a good drawing of that. But a vertical asymptote would do the same. Or just a blank graph, I suppose, would hit the mark. So C of 3 exists, but the limit doesn't exist. Oh, okay, well, I mean, we could kind of start with the same idea. The limit doesn't exist, so I'm just going to draw, kind of a graph approaching two different things. So I've got some here and there. But C of 3 does exist, so I just need it to be really anywhere. I think it could be here, right? That would be fine. It could be in at the other spot. That would just really be the difference in if it was a piecewise defined function, the little domain indicators on the right being less than versus less than or equal to, or greater than versus greater than or equal to. All right. Part D, the limit exists, but the function does not. Okay, well, it's probably easiest to start these drawing with the limit. So the limit is doing one thing, from both sides we're approaching the same value. But the function itself does not exist. Okay, well, as long as I don't fill in that circle, or fill in anywhere here at x equals 4, that will fit the description. All right, the limit and the function's value both exist, and the limit is equal to the function's value. Okay, that's something that we're going to be talking about, not next class meeting, but the time after that. So I'm just going to draw it, and now this is something that I thought was very noticeably absent in AP Pre-Calculus last year. This is terminology, because when I have taught pre-calculus in the past, and I mean even college algebra, when I took it, there was a lot of talk about this word. Okay, but either way, the function's limit exists, and the function's value exists, and they're equal. Okay, that's what we would call continuous, or what we're going to call continuous here in a couple of lessons. But that might not be something you've heard. I don't know that I've talked about it in, I taught Algebra 2 the year before last, and I don't know that we talked about continuous and discontinuous. Okay, number 5. This does not have anything to do with limits. Okay, I stole this problem from somebody else because I really liked it as, because we're right here at the very beginning of our school year. So it's never a bad time to practice some of these algebra things, these exponent rules, because this is actually going to be a pretty big deal in AP Calculus. Okay, so if we're squaring 4x cubed, what's going to happen is I'm going to take a 4x cubed and I'm going to multiply it by another 4x cubed. Okay, and that's going to end up being 16 and 6 total powers of x, right? Because when we're multiplying two things with the same base and different exponents, we do add the exponents. And you can see it on the 4's and you can see it on the x's. Okay, we're going to see that again. 4 is going to stay the same, right? There's no other number to multiply the 4 with. 3 powers of x multiplied by 2 more powers of x is going to be a total of 5 powers of x. 1 over x, we're going to write that as x to the negative 1. I don't think I necessarily expect you to know what power functions means. That's just it's the proper terminology. I just want you to write it, with exponents instead of fractions and square roots. Or at least, if you're watching this video, it would be like, oh yeah, I remember that 1 over x squared, that's going to be x to the negative 2. Square root of x is going to be x to the 1/2 power. Cube root of x is x to the 1/3 power. And the cube root of x squared is going to be x squared taken to the 1/3 power is going to be x to the 2/3. like I said, doesn't have anything to do with limits, like not really at all what we're dealing with in this unit, but in the next unit, it's going to be a big deal. And really, once it becomes a big deal, it'll be a big deal for the rest of the course. So, okay, and something we need to be well aware of is our exponent rules for AP Calculus. All right, here we've got a graph of a function, calling it f of x. Find the limit from the positive side and the value of the limit just in general. Okay, so as x approaches 4 from above, from the positive side, cy looks like it is approaching 2. Okay, so the limit as x approaches 4 from the positive side of f is going to equal 2. And then I'm going to say that the limit as x approaches 4, just generally of f of x, one's non-existing, okay? Because the two one-sided limits disagree. So I'm going to say because, fit it in, the limit as x approaches 4 from the negative side is not equal to the limit from the right. The limit as x approaches 4 from the positive side. Okay, we can see that from the left, from the negative side, it's approaching 4. And f of 4 is equal to 4, but that's not what they asked. And they just asked for the value of the limit from the right side and just the limit. Okay, the graph of f is shown below. Find the values of f of 4. Well, I don't see any graph at x equals 4, so I'm going to say f of 4 does not exist or is undefined. And then the limit as x approaches 4 of f of x, we just need to be thinking, okay, am I approaching the same thing from the left and the right? And I am. Okay, and it looks like x equals 4, y equals 4. Okay, so I'm going to say that the limit as x approaches 4 of f of x is equal to 4, like that 4 right there. I know that might be a little confusing. But, although f of 4 is undefined because of that hole in the graph, from both sides, the output values f, y, is approaching 4 as x gets closer to 4. Okay, number 8. Here we've got a composite limit, and this is, because I am committed to a diversity of problem types and difficulty levels, I'm going to show you some difficult ones too, and this is going to be one that we're going to have to think through. Okay, these composite limits are tricky, but I really believe that it's the best thing to do to show these to you right at the beginning, let you grapple with them a little bit right now. They're not the most important thing. I wouldn't even rate them as an important thing at all in August. But I'd let you come back to these problems a couple more times throughout the year and they'll get easier. And you'll start to understand it more and you'll see that growth in yourself. So that's why we're showing it to you. But I don't necessarily need you to be like 100% confident on composite limits like this. G of x, f of 1 minus x squared, what we've got coming up next. These are tricky, I'm just telling you right now. So, g of x as x approaches 2. Well, let's just think about what's happening on the inside. That's what you want to do, one step at a time. Alright, so g of x, if we just think about what's happening to g as x approaches 2. That is going to equal 0. Okay? And so you would think, okay, well, g of x is like kind of getting towards g of 0 as x approaches 2 on the inside of this composite function, and that limit's non-existing, so this would be does not exist. But if we look more closely, g of x is not just approaching 0, it's approaching 0 and is exclusively positive. It's approaching 0 from above. So what's really happening is, let me draw a picture. So thinking about x approaching 2 from the left, g is going from 1 to a half to a third to a fourth to really small numbers, getting really close to 0, but not actually reaching 0. And then from the right, as x approaches 2 from the positive side, it goes from 3 to 2.5 to 2.1 to 2.01. And the output values are getting closer and closer to 0, but never actually reaching it. So I might say that g of x as x approaches 2 is approaching 0 from the positive side. Okay? It's the best explanation I've got for you for right now. I mean, I don't want to get too deep into it. If you see what I'm saying, great. If not, no big deal. So the limit, as I'd be happy to discuss it further or not, because this is just like, maybe one question on the quiz, maybe one question on the test, right? Okay, as x approaches 2, g of x. Really think about as x is approaching 2, this thing right here is approaching 0 from above. Okay, so as x approaches 0 from above, g is approaching 4. As a result, this composite function is going to approach 4. Okay? You can make a little table of values and think of g of 2.1, g of 1.9, and maybe go even a little closer, but you would see that the output values for the interior function would be very close to 0 and positive, so kind of like approaching along this angle, and that's why we're approaching 4. Okay, I'm gonna just leave it at that though. All right, y equals f of x. Its graph is shown down below. What are the values of f of 1 minus x squared's limit as x approaches 0, and f of 1 plus x squared's limit as x approaches 0. Okay, this we just need to think about the inside function because it's algebraic. Okay, so I'm kind of get you started with a sentence starter here. As x approaches 0 from the positive side, 1 minus x squared is definitely going to approach 1, right? We're getting closer and closer to subtracting 0. But if we think about what we're subtracting, as x is not equal to 0 but close to 0 from the positive side, we're going to be subtracting a really small positive number. So we're approaching 1 from below. And then I'm going to say also, as x approaches 0 from the negative side, 1 minus x squared, well, I'm going to be taking x as a very small negative number as x approaches 0 from the negative side. So 1 minus x squared, I'm going to take that negative number that's very small and I'm going to square it. It's going to be even smaller, but positive, but I'm subtracting from 1. So this is also approaching 1 from the negative side. So this first limit here, I'm boxing off in blue, as x approaches 0 of f of 1 minus x squared, kind of a different way of talking about it, say like use a stand-in variable, like call that t. 1 minus x squared, I'm just going to think of that as t now. Well, that's equivalent to the limit as t approaches 1 from the negative side of f of t. And that's something we're going to be able to look up from the graph. That's looking like a half. I think you don't really know from the graph. Oh, maybe you do. Yeah, you do. You do know it's a half because it's on a line segment. For the other one, it's going to be very similar, except because I'm adding x squared, and x squared is always a positive number, I'm going to always have, values inside this f right here that are a little bit bigger than 1 as x approaches 0. So really the inside of the function is approaching 1 from above. So I would say, and I'm going to write in the sentence above, but just after the fact. I'm going to do it a different way this time. The limit as x approaches 0 of f of 1 plus x squared is going to be the same as the limit, maybe I'll call it u this time, the 1 plus x squared. As u approaches 1 from above, because 1 plus x squared is always a little bit bigger than 1, as long as x is not 0, f of u. And so then I'm going to say that's also something I can look up from the graph, and that's going to be, as I approach from the positive side, I'm approaching negative 1, and so it's right there. Okay, but really the reason for that is I'm thinking about each of the one-sided limits. As x approaches 0 from the positive side, this inside, this 1 plus x squared, and missed a mark, is approaching 1 from the positive side. And I was saying, okay, well, just let u be the stand-in for that 1 plus x squared. Really, it's a function. And then also I'm going to point out as x approaches 0 from the negative side, 1 plus x squared is going to approach 1 from the positive side as well, because I'm still adding the square of a small number, which is going to be a positive. Okay, I think I've said enough about this one. Let's move on. Okay, another composite limit problem. Okay, I kind of wish I had just stuck to two problems on this homework, but you know, it's all good. We can keep doing this, but if you've seen enough of these and you want to move on to the next page, I would totally understand. Okay, the other pages are definitely more important than this one. Okay, so what is the value as x approaches 0 of h of x? Well, oh yeah, this one this one was particularly tricky, I thought, when I saw it on the internet. As x approaches 0, okay, from either side, h of x is approaching 2. Okay, and so what I would say here is that, okay, I would think that the limit as x approaches 0 of h of x, well, that's going to be equivalent to the limit as x approaches 2 of h of x, and that's not existing. So that's kind of my hypothesis, but I'm going to need a reason. And so I really do need to think about the one-sided limits, okay? All of the tricky problems in AP Calculus with limits, they do go back to that definition, which is that one-sided limits need to exist and agree. All right, so I'm going to start by thinking about the right side limit. As x approaches 0 from the positive side, h is approaching 2 from above. So really what's happening to h of x is this. I'm approaching 1. Okay, then maybe somehow I could indicate that that was later on. I don't know. First is regular, then second is going to be highlighter. Okay, but then the limit as x approaches, x approaches 0 from below of h of x. Okay, well, as x approaches 0 from below, regular h, is approaching 2 from below. Okay, so that means now I'm looking at this one. That limit's going to equal 4. These are not equal to each other. Okay, and I'm just going to get my answer. This does not exist. I think, okay. Yeah, okay, I can put a not equals there, and then I have not said anything that's untrue. Now, the whole not saying anything that's untrue with an equals, or I suppose a not equals sign, is something that we will discuss more at length in this class, because it's kind of like the start of really thinking mathematically, in my opinion at least. They're good discussions to have about the way we present our work, but you don't need to worry about that yet. I'm just going to say these two things are not equal, but you know, this is actually a valid statement. Okay, keep it on going. Okay, we've got a table of values and a request for a sketch of some functions. All right, so f of x, and it's all near x equals 1. So what I'm going to do is I'm just going to draw x equals 1 there. F of 1 equals 4, and the limit of f is 5. Okay, so that means, you know, I'm just going to decide that was not successful. I'm going to decide what I want 5 to be, and I'm just going to let f approach that from both sides, right? Because the limit as x approaches 1 of f exists and equals 5. F of 1 equals 4, that means that the actual value of f is going to be down below. Okay, for g, I'm going to just draw the same thing. It doesn't have to be super fancy. X equals 1, the limit of g is equal to 2, and we kind of already ran into this once with a different type of problem, but g of 1 equals 2, so I'll just go right there, and h of 1 doesn't exist, but the limit of h does exist and equals 1, and if h of 1 doesn't exist, I don't color in anything. So, okay, and then we'll limit property situation. Okay, h of x multiplied by 2f of x minus 3g of x. All right, well, all of these limits are existing, so we're just going to say, all right, well, this is going to be equal to the limit of h of x, which was 1. That's not a very interesting problem. Multiplied by 2 times the limit of f, which is 5, minus 3 times the limit of g, which was 2. Okay, 10 minus 6 is going to be 4, which was multiplied by 1. Okay, so I've got 4 there. Right, now, okay, back to some algebra. Let's find some values of x that make the equations true. These are things that we just need to be able to do in this class, and I figured now is a good time to practice. And, maybe give you a break from thinking about those composite limits too hard. All right, so e to the 2x equals 5. I want to get that x, that expression, that variable expression, down out of the exponent, so I'm going to need to use a log. And since the base is e, I'm going to use a natural log. And I don't know if I've said it in your class, but, I've said it many times, natural log is really the only log I care about. And a big part of that is, in AP Calculus, we really only worry about, except in very rare situations, exponentials with base e, and really exclusively logs with base e. So I'm going to take the natural log of both sides. A natural log of e to the 2x, well, that's what exponent do I put on e to get e to the 2x? That's 2x, or you could look at it as their, inverse functions and undo each other. But I just like to think about it more fundamentally. 2x equals the natural log of 5, and then I'm going to divide both sides by 2, and that's going to be x equal 1/2 of the log of 5, natural log of 5. Okay, and I don't remember. I think that wouldn't, maybe that wasn't far enough for AP Pre-Cal. Like you had to turn the 1/2 into an exponent of the 5 and call it a square root or something. We don't have to do anything with that in this class. 1/2 of the natural log of 5, that's a perfectly fine answer for us. And if we're trying to get rid of a natural log in an equation like we see in the middle, we're going to use a, take e to both sides power type trick. And that's going to equal e to the 4. Okay, now e to the natural log of x minus 1, you could think about it, in terms of what a log means. It's a special exponent, and that natural log of x minus 1 is the special exponent you put on e to get x minus 1. So if you use that special exponent, you should get x minus 1. Or you could just say that e and natural log undo each other. I feel like that's somehow less powerful of an understanding. So that's 1 plus e to the 4. All right, and then this last one is just a nice second-degree polynomial. We know how to solve that. We got to start by setting it equal to 0, though. That's my first message for you. There's going to be a lot of setting things equal to 0 and solving, and in the event that they are polynomial, we might need to be able to solve them without a calculator. But the good news is the types of factoring we have to do really are not that bad in this class. It really is just like greatest common factor, like this 6 that's common to all three terms. And then, kind of your old-fashioned Algebra 1 type factoring, what two numbers multiply to -2 and add to -1. Okay, well, numbers that multiply to 2 are 2 and 1. So if this is going to work, it's going to be t and 2. I think the 2 would want to be the negative and the 1 would be positive. Okay. So I've got this factored up. I'm mentally checking, at each step, and that's what I recommend you do. Once you get to the point where you're really confident with your factoring, you should factor, and then you should mentally, distribute, think about, and realize I did it without saying, looking at 6t squared minus 6t minus 12. I'm going to look at that and make sure I didn't make an error and have to, embarrass myself on video. So I'm going to just visually double check, and then t minus 2, t plus 1, I'm saying t squared negative 2t plus 1t. Okay, this makes sense. Minus 2, yeah, okay, I'm good to go. Okay, so if I'm looking for the solutions, okay, it's one of these things is equal to 0 if their product is 0, so either 6 equals 0, which sounds unlikely to me, or t minus 2 equals 0. Which would happen when t was equal to 2, or maybe t plus 1 was equal to 0, and that would happen when t was equal to -1. Okay, so this work's looking a little crowded, so I'm going to just box the answers for each of the problems. And just a word about boxing your answer, it is not something that you have to do in AP Calculus on the free response. It's something that you are able to do. It does impact the scoring, but in a way that I would discuss with you if you wanted to, completely separate to what we're doing here. All right, so the last question we've got is just find the value of the limit as x approaches 2 of f of x for these different functions f, and it looks like they're all trig. And really, I just wasn't going to let you do the first homework of the year without interacting with the unit circle at least a little bit. It's not going to be the biggest deal in AP Calculus, but it's going to be a deal that we have to be able to interact with here and there. All right, so these functions are all nice and smooth. They have good graphs. Tangent has some vertical asymptotes, but I'm not taking you anywhere near there. I just really want you to figure out some unit circle values. All right, so the limit as x approaches 2 of f of x, and kind of the thing I would the message here is that if there's nothing bad going on with the function near the x value, like sine of pi over 4 times 2, that's sine of pi over 2, we can figure that out. We can just plug in on the function. So that's going to be sine of 2 pi over 4, which is sine of pi over 2. All right, well, pi over 2 is up here, and that's at the very top of the unit circle, which is going to be 1 unit away from the origin, positively away from the x-axis, so that's going to equal 1. Okay, then for this one, this limit as x approaches 2 of f of x, that's going to be cosine of 2 pi over 3. I'm going to take that first, and then I'm going to subtract 1. Okay, so I just got to think about where 2 pi over 3 is. I think this is actually the second time on this problem set where we've had to interact with 2 pi over 3. It's up here, 60-degree reference angle. Okay, so 1/2, it's going to be negative. That's going to be the root 3 over 2, and this will be 1. Okay, but I think the last time we were looking for sine. So cosine is adjacent over hypotenuse, negative 1/2 divided by 1. That's negative 1/2 minus 1. And actually, this is a safe place to stop for AP Calculus, but I'm going to keep going because I know that this is negative 3/2. Negative 1.5 also works. I would really encourage you not to use a mixed number, though, in this class, because if you write negative 1 with a 1/2 next to it, that could very easily be read as negative 1 times a half, if you think about it. So mixed numbers really not the way to go in this class. All right, f of x equals 2 tangent of pi over 6x. I mean, I'm not saying I won't know what you mean, but I'm just saying it could be, you know, very clear. And mixed numbers aren't always that. So this one's going to be tangent of, or 2 tangent of 2 pi over 6. That's going to be 1 pi divided by 3. Okay, pi over 3 is in the first quadrant. That's pretty high up here, 60-degree reference angle. I've got my diagram, it's 30, 60, 90, so the short leg is a half, the long leg is root 3 over 2, and the hypotenuse is 1. Everything's going to be positive. Tangent is opposite over adjacent, so root 3 over 2 divided by a half. Okay, so 2 times tangent is opposite divided by adjacent, so I'll flip and multiply. Okay, cancel off the 2's, and I'm going to have 2 root 3. All right, and that's going to be all for this problem set. I think this was a good representative set of problems. If you need more work with the limits or whatever, just go look at any of my other videos kind of on this topic. I've got plenty of practice problems. Okay, so that's all for this one. Thanks for watching.